Thank you. It's very late in the day and people have been exposed to very large numbers. So to prevent cruelty to people, I'm restricting the output of everything I talk about to a small number of bits. So XKCD is a big source of wisdom, and I try to find introductions to all my talks in XKCD. But somehow it turned out that they didn't talk too much about cryptographic hash, but this came close. Basically, encrypted laptop victim. The nerd thinks that the laptop is safe. In reality, a $5 wrench will solve the problem. But the real reality is that nobody actually cares, and you don't really get a good wrench for $5. Now, how does this tie with cryptographic hashing? Because once the password is extracted from the victim, you need to hash the password, and the password needs to be verified. Okay, sorry about that. What exactly is a cryptographic hash function? So to start with, it is basically a mapping from an arbitrary length bit string to a fixed length bit string. So the arbitrary length bit string I normally call message, and the output is usually called digest. But this function has to have some interesting properties to classify as a cryptographic hash function. One is it is extremely easy to calculate it one way. It is extremely hard to push the output from the wrong end of the funnel and get the input message. Computing the inverse of a cryptographic hash should be very hard. And number 3, and this is the most important thing, given 2 separate bit strings, it is extremely unlikely that they will have the same mapping. So there are many standard cryptographic hash functions, and one of the defining characteristics is how many bits is the output. So MD5 has 128 bits, SHA-1 has 160 bits as output, and SHA-2 has a set number of bits as output: 224, 256, 384, or 512. We see this story over and over again, that somebody defines a new hash function, and breaking hash function is a contact sport among cryptographers like my co-author Stuart Haber, who is sitting right here. And one might wonder, why is this important? Turns out that hash functions are used for fairly important things like certificates, and when a certificate is presented to a machine like a Windows laptop, the laptop tends to trust the code. So quite recently, there was a malware called Flame that was created by a nation state. It did many wonderful things. In terms of malware engineering, it was superb. It was one of the best and most sophisticated pieces of malware ever written. But what's relevant to our talk, they used what's called an MD5 collision to create fake Microsoft certificates. And they used these fake Microsoft certificates to present themselves to Microsoft laptops and run as trusted code. That was a beautiful piece of engineering, but worrisome if you are in the business of designing and defending these things. So there is this big saga which I realize is almost unreadable on on the screen. But the screen basically consists of various different hash functions. Where you see a skull, it means that the hash function is so easy to break that it's that many people have published many papers on breaking them. When you see a plus, there is a theoretical weakness or flaw in the hash function where you do not even need to resort to brute force or do enough computation to do the birthday attack thing on the hash function. The ones with the magnifying glasses are ones which are not broken yet, but researchers have studied slightly weaker versions of those hash functions and have characterized how much effort will it take to break these hash functions. Just I'll try to go over things very quickly. One of the questions you might ask is, if we are all cryptographers, I mean, if there are so many good cryptographers, why do hash functions keep breaking? So this could have been something from a stand-up comedian, but this is actually from a PhD thesis on breaking hash functions. And it describes what hash functions look like under the hood. So it says, oh, pour initial value in a cauldron, add salt, stir well, break it into 4 pieces, make sure that the 4 pieces are the same length, then stir based on values of some constants and so on and so forth. This looks like a joke, but this is a almost technically accurate description of MD5. So let's take a slightly deeper look as to why things are the way they are. Let's look at the SHA-1, which is one of the first secure, it's the second function in the secure hash family. What kind of gadget does a hash function have at its core? I don't want you to memorize this picture, but I want you to note that the internals of a hash gadget are fairly simple. There are shifts happening, there are 32-bit additions happening, and there are some bit rotations happening. And if you see, there are inputs which take a block of the input string, and there is a KT, which is a constant that is applied to this gadget to make it behave in a certain way. And how do hash functions work? You take these gadgets, you line them up, you chain them, you take the message, break it into blocks, line up the blocks with these gadgets, and let the magic happen. You might ask, what's wrong with this? Nothing fundamentally wrong, except if you're an attacker trying to find some weakness in the hash function. Stuart, keep me honest. You could find a weakness in one of these units. Basically, you could keep everything else the same, and if you find 2 different inputs that cause a collision in the chaining value, you are basically done. So this opens up a door so that you don't have to do a complete brute force attack on the hash function. So when you are constructing hash functions, you have to be wary that these things don't happen, that breaking each of these units should be hard enough. So SHA-1 has a known theoretical attack cost, if you look in Wikipedia, it will say that if you spend this many dollars, it's the order of $1 million in cloud time, give or take $1 million. You can find a hash collision using SHA-1, and you can use this collision for things which might which you might use profitably and earn a better return than the $1 million you put in. So SHA-2 is the next in this line. The bit arrays of each of the gadgets gets wider. The expressions get a little more complex, and if you look in at the description of SHA-2, there are there is a pre-calculated amount of work you have to do to break either the pre-image resistance or collision resistance for SHA-2. So basically, everyone knew that SHA-2 is not broken yet, but given enough computation power, it is bound to happen, and hence NIST had a contest for the latest, greatest hash function, and the winner was something called SHA-3. And the SHA-3, it was not officially called SHA-3. The authors called it Keccak. And if you see, so far I showed you that hash functions are created by arranging gadgets in a chain and letting values pass through it. In addition to that chain of blocks, chain of gadgets, the authors of SHA-3 presented a generalization, and this generalization is, instead of arranging these gadgets in a chain, you could arrange super gadgets in a tree, and that they call Sakura. One of the things you should know about Keccak is that internally Keccak is a fairly flexible hash function. That is, you could tweak the creation of these gadgets to decide to yield a required number of bits in the output. So out here, R and C, R is the routing bit and C is the capacity bit. You could shrink R and get more C, or you could shrink C and get more R, and there are some engineering trade-offs that you have to do to get a flexible output hash function. Anyway, I won't go into this in much greater detail because I want to get into the actual meat of the talk. What is the big deal about Sakura? The nice thing about Sakura is that it is a tree hash mode where you arrange your computation in a tree, and it's more flexible than other tree hash modes. Most other tree hash modes required you to arrange your computation in a fixed shape tree, whereas in Sakura, the shape of the tree is under your control. If you are the one creating the hash function, that is. And this kind of Sakura tree is parameterizable. The hash function that it uses to hash little blocks of your input is parameterizable. So you could take, say, SHA-384 as your inner hash function, or you could take your favorite new latest greatest hash function, and you could still use that with Sakura. You're not restricted to just using Keccak. So basically, a Sakura is something that takes a mode. A mode is something which tells you how to shape the tree. It takes an inner hash function, like your favorite hash function, say SHA-384 or Ketchak or something, and it takes an input and it returns a hash value. Now, why am I giving this talk at all? The Stuart and I basically saw an opportunity here. And the big opportunity was that even though Sakura was announced by the Ketchak authors fairly early in the game, not a single implementation of Sakura exists in any language. I might be wrong. If I'm wrong, I would welcome the correction. The second thing that the Sakura authors had intended to do perhaps, but left out, was how do you communicate about the shape between the person who computes the hash and someone who verifies the hash. So this was a double opportunity, no implementation, a conceptual gap. That's why both of us decided to do it as a 5%, 10% or night and weekends project. So what is our contribution of this talk? We flexibly express tree hash modes, that is, we decouple the shape from the implementation of the hash function, and we arrive at a simple, easy to read implementation of tree hash mode that others can play with and improve. Now, a little bit of tree hashing. What exactly is tree hashing? So far, I hadn't said anything about it. Basically, it was introduced by Merkle and his co-authors. The idea is that you should be able to keep the hash of a bunch of things as leaves, and you should be able to authenticate any leaf by just starting the computation of a hash at a leaf and then go one step up at each time. At each node, you use the newly computed hash of the leaf that you're verifying and the other sibling hashes which you have already stored in the hash tree. That's a very simple idea. What's the big deal? The big deal is the same string can map to different shapes. How do you break the string into trees? So if you had a string ABCD, you could arrange it in either as the first kind of tree or the second kind of tree. Remember, in the history of broken hash functions, we do not want to introduce a stupid way of breaking a hash function. And the stupid way of a hash function, stupid way for breaking a hash function would be to introduce stupid collisions in the tree hash mode. So out here, for instance, if you had the string ABCD and the hash of A concat B is H, then ABCD and HCD should not have the same tree hash. How do you ensure that? So this work was actually done by the creators of Sakura, and they introduced something called padding. That is, you could recognize where the bits came from just by looking at the padding bits. So you could distinguish leaves from non-leaves because leaves had a particular padding. You could distinguish output of a hash computed somewhere in the interior from the root, because the root and the interior have different padding. When you concatenated things, into a string, the act of concatenation had a different padding. I'm simplifying things a bit, but the Sakura paper was very rigorous. And the ask of this tree hash mode is this. Whenever you have a node that computes a hash function, you should be able to decompose the inputs to this hash function right to left just by looking at the padding bits. And this decomposition should be unique. So along with the unique decomposition and the security of the hash function, you could prove this. You could prove that Sakura is correct purely by induction. So now we jump to the implementation. And what are the goals of the implementation? Okay, we know that Sakura is correct, but we need a way to decouple the shape of the tree from the implementation of the tree hash computation. Number two, because I'm a very lazy reader of code, the implementation of this must be understandable and easy. Sakura had a couple of goals. One of the goals was that it enables incremental hashing, and the second explicitly stated goal was that Sakura should make hashing friendly to multicore parallelism. So our implementation of Sakura tree hash should be friendly to multicore parallelism. And the last goal, because this was a 5% project, having a good performance and scalability is nice to have thing. Nobody was breaking down the door to demand good performance. What were the non-functional requirements? You want to do things like avoid zero null confusion. I am a lazy programmer, so I don't want to do boundary checking. But other implementations of SHA-2 have had the boundary checking thing wrong, and that has resulted in some vulnerabilities that are well known. Initializing arrays is a problem, and there have been implementations of SHA-2 where because the initialization was done wrong, you get wrong results, and this result, this bug was not found for many years. There was another bug in an OCaml library that computed SHA-2, where something was nulled wrong. Instead of say x being null, star x was being null, or vice versa. Don't ask me for details because I get the stars, ampersands, everything completely wrong. And length parameters can lie. That is, in C crypto functions, it's standard to say, okay, here is a function. This takes an array, and here is parameter 2, which says how many bits are in this array. Of course, you could get the number of bits wrong. Your function will work happily and do the wrong thing. And because you and I use the same function, the hash computed by me will be verified by you properly. So the bug won't affect most of the people. Okay, enough of this. And because I want things to be multi-core friendly, these are other things I want to avoid. Hyphen bugs, which is basically I start running it, I find a bug, and then I run it in the debugger, and I don't find the bug. I want to avoid race conditions, and I want to avoid all the other things that come with doing multi-core programming wrong. So there is one other wonderful thing about Haskell. Haskell is one of the few languages where literate programming is simple. That is, you can write your code as a literate programming mode, where where the main body of the stuff that you write about it in is in LaTeX, and the code is in Haskell in the big bracketed by begin code, end code. So I tried literate programming for a change, and this implementation is done in the literate programming style. So I'll go over. So we need a definition of shape. Basically, if Sammy is verifying the hash function and he's using my code to verify it, and I have computed the hash, I need to tell Sammy what shape to use to verify the hash. And what has happened is because I switched from PowerPoint to Beamer, the display is showing the wrong slides. My page downs the PowerPoint, but not that was not my intention. So I have to go to the extend mode. No, I have to go to the duplicate mode, and so you were witnessing a premature demise of my talk, and I apologize for that. Okay. So here's the definition of shape that I started out with. For now, let's ignore the interleaving completely. Let's assume that before you start computing the hash function, you know the length of the string that you are computing the hash on. So it's a simple tree hash computation. You know the string already, and your first job is to, given the length of the string, you have to create an entity called the shape, which describes how to draw the tree over which you compute the tree hash. The data type for shape basically has the following constructors. The first is the inner hash. The inner hash corresponds to a node over which the inner hash function is computed. The second type is concatenation of a bunch of edge shapes, which is basically a list of things that you have already computed, and you are just concatenating them. Let's forget the interleaving for now. Then I have a constructor called slice, and the job of the slice is to take the input bit string and take a slice of the input bit string. And the last constructor is a pad, which lets you shove a few bytes at the end of a bit string, so that you can do the padding right. Or the beginning, yes. Thank you, Stuart. So one thing I haven't proved yet, but I can wave my hand very vigorously and say is that this description of shape is complete with respect to the Sakura specification. That is, anything that the Sakura authors, all the modes that the Sakura authors showed in their Sakura specification can be expressed by using this shaped data type. Okay. Now let's just go ahead and compute the tree hash. So here's the serial tree hash, which to get everything to fit on the thing, I named the function with one character, s. It takes a hash function, which is the inner hash function. It takes a shape, and it takes a bit string, which is the input, and returns the bit string, which is the output. This is all very simple. I told you this was a very introductory talk. So if the thing is an inner hash, all you do is you compute the hash function on it. You compute the hash function, but you push the computation of the tree hash inwards down one level the tree, and then compute the hash function on the result of what you got. If the shape is a concatenation, you apply a map of the tree hash to everything and concatenate the results. Any questions? I'm going over this very fast, so if there is any confusion, you must clear it now. There is only one way to consume an input string, and that is to evaluate the shape called the slice. And when you see a slice shape, what you do is you take that chunk from the bit string and a pad basically evaluates to its argument. So it's like shove the bit string immediately. So now, where do you see any opportunity for computing things in parallel? I see only one place, and that is when you are applying this map of the tree hash onto the list of things, you can parallelize this computation. Computing things in parallel is a very subtle and very deep topic, which I shall not cover in this talk. I use the book by Simon Marlowe as a Bible, and I've tried various things. But for the purposes of this talk, I shall say that replacing this map by a suitable incantation that does things in parallel is the ideal result that I hope. And here it is. So to convert that serial implementation of tree hashing into parallel, I had to change just one piece of code, and that is to replace the invocation of map with the invocation of something called the strategy called pair map, which takes a strategy which says evaluate things in parallel. The rest of the code remains the same. So if you believe all the things that are good about Haskell, you can convince yourself that your serial implementation and parallel implementation are pretty much doing the same thing. And also, if you wanted to convince yourself that this tree hash is doing the right thing, you could walk over these pattern matching cases and prove to yourself by induction that the tree hash is being computed in the correct way. So what did I completely gloss over? I glossed over this. How do you compute shape? how do you, shape is a function, so in Sakura, shape is a function of the length of the input string, and how you convert the length of the input string into a particular shape is what the Sakura authors call the mode of the Sakura computation. So they give some example modes, and one of the things I did in this implementation is try to go over as many modes as I could. So I'm very bad at giving names to functions. So so basically, one of the first and simplest modes that was in the Sakura paper was basically to convert things into fixed length chunks and have the last block as the remaining thing. So this to do the tree hash our way, you had to do two things. You have to take the input string, convert it into a set of shapes that represent the fixed size chunks and the optional end chunk in case there is a remainder of bits. So this is a fairly simple function that given a number converts given a number which is how big each chunk should be, and the second number which is the size of the input string, and two things. One is a pad which corresponds to what the inner hash computations have to be padded with, and the second one is the root pad, which is what do you pad the final computation with. It computes the shape, and this is the since I have only 10 minutes, I'm not going to go over this code, but it's rather simple. It's okay. What I'll do at this point is I'll stop talking about the code and show you some of the things that makes me really happy that I chose Haskell to work with. In this implementation, Stuart and I made no attempts to optimize anything. We did not try really hard to worry about, oh, is this way of doing slice, is this way of converting some, picking the shape, is it scalable or not? But when we actually ran the benchmarks, we found that, so this, remember, I see multicore papers which start with the thing that, this kind of multi-core scaling technique is bad because it doesn't scale beyond a few thousand cores. I'm not there yet. My heavy desktop with 70 something gigabytes of RAM has only 12 cores. So I could just verify scaling up to that. And if you see, so these lines correspond to different block sizes I chose. So things are reasonably understandable if you stare at it a little bit. So the top one corresponds to the case where we chose a very small block size. And because we chose a very small block size, the shape was a giant tree. And because the shape was a giant tree, there was a massive number of times the inner hash functions were called, which is actually a very stupid thing to do. But because you had that many things being done, it enabled fairly nice scaling up to 4 cores. and and beyond 4 cores, the scaling was less impressive. And finally, when I went from 11 cores to 12 cores, I guess the task of running the operating system or whatever the 12th core was doing increased the cost of things. So as I had bigger and bigger blocks, the amount of work reduced, but the scaling started tapering off much earlier. So as you see, I'm using out here in our code, what we are using is the eval monad and strategies. We haven't yet experimented with the other multicore techniques, like using the pair monad that gives you a much finer degree of control over what you're doing. So that would be among the things we would investigate next. One other thing that I glossed over was I asked you to forget about the interleaving. On a careful reading of Sakura paper, it turns out that one of the cases that the authors had in mind was when you are hashing a bit string where you don't know the size yet. So I have some preliminary code that I'm too embarrassed to share, which basically achieves the same effect by creating a lazy shape and using the interleaving constructor. Basically, the nice thing about Haskell is that whenever you have streaming and you have a shape that doesn't depend on the number of shape, which is not a function of the input size, but can be computed lazily, the interleaving mode works very well. So, okay. The future work is I need to enable incremental hash computation. Say, suppose you are trying to use this for GitHub, and you want to store the intermediate hashes, the shapes, and stuff in some nice way. How do you organize the storage and plumbing around the whole thing? Lazy shapes is something I'm working on. As you see, the scalability of this computation was not stellar. I ran some profiling under thread scope, and I found that one of the things that chokes the scalability is at least what visually looks like stop the world garbage collection. That is, when garbage collection kicks in, every core seems to stop its computation. I need to drill into that more. I need to understand what are all these parameters that go with that RT plus RTS N2 and so on. If there is anyone in the audience who has used the garbage collector in GHC in a much cleverer way than me, I would like to talk to them. The final thing is we are in contact with the Sakura authors, but with the very great latency. So I need to talk to them more actively and get their input and get input from other people as well. So if you have any questions, I will either answer them or I'll volunteer Stuart to do so. Simon Marlowe, parallel and concurrent programming using Haskell. Stuart is reading my bag. I hope he doesn't find gremlins before he finds the books. That one. Yeah, it's a really good book. I strongly recommend it. Yeah. Yeah. I'll I'll work with you on that. Yeah.
Just a quick question. For third presentation, and if you had some of your goals as performance was one, I think that would be great on a lot of applications, but from a security standpoint, isn't that also kind of a weakness if you make it too fast? Because you can just kind of start more combinations quicker?
Are you the defender or are you the attacker? Yeah. So, uh, the forward computation, that is the computation of the hash, is meant to be fast and easy computation. It is the reverse computation that's meant to be difficult. Hmm. 160. The birthday attack. Yeah. Hmm. And yeah. So I used PowerMap for doing embarrassingly parallel calculations for simple things like calculating Fibonacci stupidly and calculating the kth power of a big basket of numbers and adding them. So I'm not qualified to answer that question. Yeah. Uh, but I believe that if you use primitives that offer you finer control, like the fork join parallelism uh, that comes with other libraries, you will get better performance. But I don't know that firsthand. It's not hackage worthy. I have a gist that I put on the Meetup thing.
Can you post the slides on Meetup too as well?
Yeah, yeah, I will. I will.
The slides are there.
No, I will post it. I was still editing the slides on the train, so. Yeah. Okay, I'm done, and